Hi everybody, my name is Mickael. I've been a tech lead in Komodor for the past almost 5 years now, and what we're trying to build basically is a day 2 operations platform to make Kubernetes more accessible for everybody. And today I'm going to be talking about how to better understand the data that Kubernetes provides in regards to reliability, and our approach as a development team and experts in Kubernetes, as we think we are, to make it more insightful to both users and operators of clusters. So if you've ever wondered how to fix all the problems you ever had in Kubernetes, this is probably going to be interesting for you. And well, sometimes I think it's not just about having the data to troubleshoot things, but it's also how you use the data that makes a great impact. So let's get straight into it. If I can figure out the clicker. I can. All right. So first of all, let's talk a little bit about what we're talking about. So Kubernetes is an infrastructure layer on top of applications or your workloads. I think that you all know of that. And when I'm going to say signal, it's basically a piece of information or a piece of data, some kind of hints that we're going to use to troubleshoot and understand what's happening inside our cluster, inside our services. So simple signals that Kubernetes provides out of the box can be, for example, statuses, events, some kind of metrics, logs, etc. And more sophisticated signals, that's what it is that we're going to use to actually troubleshoot our issues, require more effort to actually pull off. So if we take, for example, the simple signals that or piece of information that Kubernetes gives us out of the box, and we look at them over time, we try to correlate them between different pieces of resources and across clusters or environments, then we get what we call reliability insights. And that's something I'm going to touch again in a few minutes. So the ecosystem around Kubernetes has evolved a lot over the years, and we've developed as developers or as tech guys different approaches on how to troubleshoot and understand what is happening in our infrastructure, in our workloads and services. And here are 4 main approaches that I think that are relevant for everybody. One would be analysis of a timeline. So basically check over time data that we get from our workloads and try to understand basically if we can see any kind of trends or any kinds of just outliers that are happening that can point to an issue. The second thing would be to try and analyze correlation of different pieces of data, different resources. For example, if you have a workload, a deployment, let's say, most likely it will use some kind of configuration, like a config map, a secret, an ingress, volumes, things like that. So we can try to basically match all the things that work together as one to get an idea of what went wrong over time. Then clustering analysis is basically trying to group together unrelated things that are in your clusters. And you'd be surprised, but there's a lot of it. Sometimes things start to fail and you don't know why. And it's something that you wouldn't even think about it. So this is basically one of the approaches to try and kind of group anything into logical beings that can make sense together and try to understand the data that way. And of course, last but not least, there's always misconfigurations that can be very costly. Sometimes you update some kind of config map and the slightest change over there can just mess everything up, right? So at Komodor, I think that we're in a great position to take all these approaches and figure out what works the best. This is a very simplified diagram of how Komodor works in a nutshell, but we, as a company focusing on Kubernetes operations, we ingest a lot of data related to Kubernetes. And the way we do that is we listen to the API server, we listen to the metrics, we watch what happens on the cluster, and once we have all that data, so it can be just Kubernetes events, changes in resources, basic CPU and memory usage of all your containers and workloads. A lot of things can come off from Kubernetes that it gives you out of the box, but everything is very basic and everything is very disconnected. So we create what we call synthetic events. A synthetic event is essentially just all of what I told above, just together, kind of refined data of all the basic signals that Kubernetes provides you. And once we have that, we persist the data and we show it in our platform. And we were interested at some point to try and kick off a project called Reliability Insights. Basically, we wanted to understand what Kubernetes provides and how we can make it better for the end user, for everyone basically using Kubernetes, to kind of help them fix their problems on the cluster, right? So first of all, reliability. It's, by definition, the quality of being something that we trust or something that is consistently performing well. And at least in my opinion, I think that that's how I like my Kubernetes clusters, consistent and trustworthy. Sometimes it's not always working that way, but that's what we can do. And to be able to achieve that, we've set up a little experiment lab, kind of. Very basic thing where we took some Python script. We've connected some data sources from data that we already had. And we just worked our magic and kind of played with the data a little bit, see what we can connect, see what we can understand from it, and just output that to a terminal and kind of play with that and see what we can determine as useful, right? And I'm going to go over some of these examples that have succeeded, that have failed, and go over them, talk about a little bit what are interesting about them, how we did all the interesting connections between the data and the correlations and analysis, and maybe it's something that I hope will be useful to you as well when you're troubleshooting your next issue on our cluster. So the first one, I think that everybody has encountered at least one container restart in their lifetime, and it's something that happens quite often. And because Kubernetes is an orchestration platform that kind of handles the lifecycle and kind of auto-healing of your workloads, this is something that's normal, this is something that's fine, but when it happens 200 times over the span of one day, that's when you get to start to worry a little bit. And for example, there was one service that we developed at Komodor, and one day one of the teams just comes to me and they ask me, listen, I'm not sure what's going on, but we try to access the API of this and that service, and we just get a lot of 502 responses. It's not working properly. We need that fixed. So, of course, I went and checked kind of the metrics and what happens with that service, and I saw that starting at a certain day, the container of that service was restarting again and again and again. And if you can see on the end of that graph, it started happening more and more often, right? And so every time this happens, basically, the load balancer that was serving the request was not aware that the container was restarted that abruptly, and it takes him a few seconds to understand that and kind of not forward the request the next time. So it causes failures. But what's interesting here is the density of restart that happens over time. And even though Kubernetes actually gives you these metrics, your container has restarted 1, 2, 3 times, or like 24 times in the past minutes, at some point Kubernetes kind of deletes that data, right, if you watch the events, and you don't have access to it. But without being able to look at it on a timeline over time, over a long period of time, actually, then this data becomes irrelevant most of the time. The next thing is that sometimes you need to look at multiple pods or containers together at once, because when you're running a workload that has 200 replicas, looking at just one of them specifically will tell you virtually nothing. And looking at the memory usage here, for example, we had, I think, 60 or 70 replicas for that service, but most of them were okay, but it was just a few pods that somehow were just load balanced, not in the best way. And most of them were getting a lot of out-of-memory errors, and that's why they restarted. And getting all that data together on the same timeline and seeing them one next to another, that's what helped us determine the cause of that issue. And while it's simplistic, it's something that still, if you don't have access to the tools and the right data, it can take you a few hours, a few days to kind of get aware of that. And so the fix is very obvious. We just give it more resources because it's a memory-intensive service, and that fixes the issue. The next one is about HPA. So a lot of you probably use horizontal autoscalers to kind of scale whenever there's more load or peak on the system. But here as well, we can see, for example, that memory utilization is always kind of staying near its limit. And what that says to us is that we're also reaching the limit of the HPA, of what we declare that the HPA should scale to. And that means that it's not going to perform as well, because if it was scaling at that point, then the memory utilization should go down because there's more replicas to kind of spread the load around. But if it stays around 70%, which that was the target value, that means that we have the maximum replicas we've given that HPA, and then we can't really scale anymore, right? So any more load from that point on will just cause our system to be unstable. And again, this is something that I feel is hard to look at when you're just looking at kubectl or different tools like that to kind of understand what is the status of a autoscaler. But when you watch the data over time on a graph, something that kind of is able to show you the metrics in a proper way, then you understand the issues a lot better. Another example here is about CPU throttling. So CPU is not going to kill your application, but it is going to kill your business. And what we see here is that 62% of the time, this application was throttled. That means something was being late to respond, something didn't work properly, some calculations were taking too long, whatever it may be. But when you do kubectl top pods or something like that, and you see, oh, it's using 100% CPU, you're probably thinking, that's momentary. But if you see it happening 60% of the time, like most of the day, something is wrong. You need to scale somehow, you need to fix your application, something needs to be done, and that's an action we can do. Now, here's one a bit controversial. It depends like what you do for Kubernetes. But for cluster operators, for example, that have to maintain and kind of keep everything working and up to date, they know how valuable this is. So Kubernetes, they ship out a lot of new versions, new APIs, new features a few times a year. And if you don't keep up with it, you're not going to get security upgrades. The cloud provider will stop working with what you have. And so you have to do it. But every new version will introduce some deprecation to existing APIs, some existing resources that you might be using. And if you're using an API resource that is getting deprecated, something might break in the process of upgrading. So you might go from one version to a newer one, and then things stop working. Or for example, there are some feature gates in Kubernetes that might be enabled in a new version that just will change how things work for you, and that's not expected. So this is a very simple one, but basically we can try to stay on top of it and get notifications or reports on if I upgrade to this version, what is going to be affected in my cluster. Most of the time, nothing is affected, and then I'm happy. But the one thing that can break, and then I'm extra happy that I know this. And this is one of my favorite ones called the noisy neighbor. That's how we call it. And basically, it means that there is one service or one workload affecting another one. And this is the kind of issues that are very, very hard to troubleshoot and determine the root cause of. And when you're able to take a lot of metrics, a lot of data points, and correlate them together to understand the relation between them and how they work together, then you're able to save a lot of time troubleshooting issues like this. So how noisy neighbor works is in usually 2 or 3 phases. Phase number 1, workload A grows in resources, and it makes a lot of noise. Phase number 2, it gets an eviction notice. Usually, the node doesn't actually give you a notice. It just evicts the pod, and then you're really unhappy. But statistically, this situation happens over a period of time, right? It doesn't appear instantly. It doesn't just, nothing just crashes abruptly. But because it happens over time, it also hides things from you, right? Because something starts happening, and you say, all right, this is an issue with A, whatever. And then B starts happening, you say, okay, there's an issue with B. But what's happening in real life is that because A is down, B is also down. And then all the letters are unhappy. The problem with noisy neighbor is that it's pretty expensive and tricky to kind of calculate and correlate from all the data points, because you need to know how everything works. And sometimes it's application specific, or like it has several dependencies that are together, and you need to be able to kind of put them together. But this is one that's very affecting everybody. On top of all the insights that were pretty interesting and kind of worked well, there are some that just didn't survive. One of them was idle workloads. So like we have a lot of throttling happening in our workloads, we also have workloads that just don't like working, they prefer to sleep, and they do nothing. Most of the time what that means is that you just pay for doing nothing. But it's something that's a bit questionable to analyze and tell you something actionable to do with that, because we don't always know that you don't actually need, or this thing is doing nothing. Sometimes you just need something on standby, and you have to have it there just because of you want to keep it kind of a hot API so it doesn't spin up when you need to. Another one is outdated Helm charts. So Helm is a great tool, a great templating tool to kind of keep revisions of your applications and in between different environments, but it's also pretty complex. And we do have an open source Helm dashboard that is separate of the product. And what it allows you to do is kind of manage all the charts that you have installed and see what happens, which values on which environments, which versions are installed, all of that. And I can tell you from experience that managing Helm charts it works, but it's not fun. And sometimes you're kind of like 2 years of versions behind of new stuff that you have installed. And at that point, it becomes very dangerous to kind of upgrade them to the latest because everything has changed. But the problem with kind of analyzing these kinds of insight is that it's very heavy to run, right? Helm charts, they can contain hundreds or thousands of resources and different versions, and it takes time to get that data from the cluster. It takes time to go over through all that. It's always encoded in some way. Sometimes it's encrypted, not always. And we also ran into the problem that a lot of people used to keep their Helm data in private repositories. And then when you're a cloud service, it's kind of difficult to access that. You have to run that locally. You have to go through something. And it wasn't worth it when we provide something free and open source anyways. So they already have that. Another one is node termination. So node termination is the notion of when a node got killed, and we want to understand why, right? So for those of you who use spots or variable infrastructure workloads like that, or node autoscaling, you know that there's a lot of disruptions happening throughout the day, and that's normal. That's just how it works. But sometimes when a node goes down, it causes issues, reliability issues. And trying to understand that one of your workloads, one of your service isn't working properly was because a node was terminated is also hard to know. First of all, how do you know that the issue didn't start before the node was terminated? Sometimes the node gets some kind of notice and says, all right, in 1 minute, I'm going to stop. So you have time to kind of get evicted and stop what you're doing. And sometimes it just goes away. And you have no idea he was even there. You don't even know that he was brought down. But what's interesting here is also seeing which workloads were affected the most when this happens, right? So we can always hook up into the APIs of the Spot instance provider, for example, and try to understand, all right, if this node went down, at that same time, all these workloads were affected, we keep the data and we can analyze that over time. And then we can understand, all right, if this service is very important to me, maybe I want to put that on a different node group. Maybe I want to balance it a bit better in between nodes and not just have one spot instance with all my databases. Don't do that. But again, this was something that was very expensive to calculate. Now, why I mean expensive, it's not really money, but time and compute. And so if it takes you minutes or hours to kind of get that indication, it's sometimes not always worth it. And you also have services that fail together. So that's very similar to the noisy neighbor, but a bit more complex. And this is one of the interesting ones. So like I said, services might have hidden dependencies that you don't always think about or even know about. Sometimes all you do is just create an app, right? But then most of the apps, they need a database. They need a cache. They need a queue. They need a lot of different things. They need internal APIs. And when one of these dependencies stop working, sometimes your app is written in a way that can recover from that, but sometimes it's written in a way that just, it will stop working. And so we developed kind of a DBSCAN algorithm over data that we have on timeline, and we are aggregating and grouping data, and then we kind of took the history of all the services and tried to merge all that together to analyze what failed together, what was correlated, what was related one to another. But one of the problems with this insight is while we knew what was depending on what, we didn't really have something that was actionable that we could tell our users, okay, you can do 1, 2, 3, and this problem will go away. So then this becomes a bit of a moot point that just, all right, you have an issue, but we don't know how to fix it, so I don't know what to do. And so this was a lot of the experiments that we've ran over time. And again, some of them were so successful, some of them were just interesting, and some of them just didn't work out. So the setup started like that. We had a Python script, we had some data sources, and then an output. Then it allowed us to very quickly execute ideas into results, and we had the freedom of doing things very fast because it was kind of separated from the product at that time. Then came the time to actually see how we can get that into the product. So we've changed the setup a little bit to kind of do a review internally, and what we wanted was to persist the data and provide a simple UI. We used AppSmith in that case to tell our internal developer teams, all right, now look at your services. We have all these super cool insights. What can you, like, did you know about all these things? And most of them, it was a quick win for them to fix a lot of small things that they just weren't aware of. And all these insights gave them a lot more freedom to continue developing new features because they knew now that they can trust their applications. And when we decided that this was ready for production, we had to change the setup once again. So we still have our data, but then we want to get it to the product. And so we have to be more reliable, more persistent, more efficient. And we try to look at what products were good to be like production grade job runners kind of. And we looked at Argo workflows and Apache Airflow and even Kubernetes jobs. But at the end of the day, these were very complex to kind of get into because we weren't using them anyways. And so we just stayed with our own solution that was just a Python script that we've kind of expanded into adding what we need to, like multi-threading, retries, priority, because we want to run something over another insight. It was more important to us, things like that. So what I want everybody to kind of get away with today is that while Kubernetes provides you out of the box with a lot of valuable information, you need to know what to do with this information, what it relates to, and how you can leverage that to make your application, your workloads, and your infra a lot more reliable. So sometimes doing all of that stuff is pretty challenging or you need to take the time to actually do all of the experimenting, but it's very useful for everybody using Kubernetes. And just one last thing is about the experiments, that it's always worth it to have a very fast feedback loop in order to get the result that you want to. So I don't have time for a quick demo, but I will refer to my friends over there if anybody's interested. And if you have any questions, I'm here. Thank you, everyone.